Okay, we are working on worksheet 5, number 1. Okay, we've talked about this diagram in class, so I'm not going to spend a lot of time talking about the different forces, but we have the frictional force here that is away from the pivot, so it causes a torque. We also have the normal force that does not create a torque because it's parallel to the radius, and we have the weight that does not create a torque because it is at the pivot. We know this angle is 30 degrees. We know that this change in height is 2 meters. We know that the mass of the sphere is capital M, the radius is capital R. We know that the moment of inertia is 2/5 mr squared, and that comes from the fact that it's a sphere. We know that alpha is A over R, probably just will need it at some point. And now we're ready to work on the equations. So I'm going to solve it the first way with forces and torques. So the sum of the torques causing rotation is just friction. So it will be the frictional force times the radius, and that equals I alpha, Newton's second law in rotational motion. So we have friction times R equals 2/5 mr squared times alpha, but alpha is A over R. And if I look at that, one R will cancel with that R, and then another R will cancel with the R on the other side. So what we have is that the frictional force is 2/5 m times A. Then we look at the sum of the forces acting on the sphere. And we only care about the forces that are going up and down the incline. And so that means we're going to have to pay attention to the fact that gravity has components. So in the sum of forces, we have that Fg in the x direction minus the friction equals ma. And capital M just because they said it was capital M for the mass. So Fgx, we have to use our angles, and Fgx happens to be the opposite side of this triangle. So we're going to say that the sine of 30 degrees times the weight, which is mg, so it will be mg sine 30 degrees minus friction equals ma. And we're going to plug in for friction what we got from the torque equation. And I'll go through and make sure all of my m's are capital. So we have capital mg sine 30 minus friction, but friction comes from the torque equation. So it's 2/5 capital MA equals MA. And now the physics is finished, but to help you go through the solution, I will go ahead and do the algebra. So the masses will all cancel. Let's go ahead and get rid of that. And then I will put all of the accelerations, all the A's on one side. So I have 2/5 plus A. So I have 7/5 A over here. And I have G sine 30 degrees over here on the left side of the equation. And I will divide both sides by 7/5 or multiply by the reciprocal. And I end up with the acceleration equals 3.57 meters in a second every second. And I used 10 for G. If you use 9.8, you're going to get a slightly different number. Now, acceleration doesn't answer the question. We need the final velocity that the sphere has when it gets to the end of the ramp, but it's important to have the acceleration in order to do that. So we're going to go back to what we know over here. And we now know the acceleration. So we're looking for the final velocity. The initial velocity is 0. We have the acceleration, which is 3.57 meters in a second every second. We know that the change in position, well, I guess we don't know that. So we got to figure it out. So let's draw a triangle. This is 30 degrees. This side of the triangle is 2 meters. But what I need is this distance because that's the distance it actually travels in the linear direction. So when I do that, sine of 30 degrees is equal to 2 meters over delta x. And that's what I'm going to call this because it was in the direction that it traveled. So delta x was equal to 4 meters. Okay, so I know delta x, I know the acceleration, the initial velocity. So now we're going to find the final velocity by using this equation. And when we plug in everything that we know, the final velocity is equal to, this initial velocity was 0, so 2 times the acceleration times the change in position, and we have to take the square root of that. So the final velocity is 5.34 meters in a second. Okay, so the other way to look at this problem is to use energy. So now if I go back to where I started, I don't need any forces to do energy. What I need to know is that this is my delta y, and it will be 2 meters. So I want to look to see which energy I have to begin with and which energy I will have in the end. No friction, so I don't have to deal with heat, although that really kind of doesn't make sense in this problem, but we'll go with it. So in the beginning, I have gravitational energy, and in the end, I have kinetic energy that is linear, and I have kinetic energy that is rotational. So now I have to go back and remember what the equations are for energy, and this is mg delta y. Kinetic energy is 1/2 mv. It's going to be v final squared since it's at the end of the ramp. And the rotational kinetic energy is 1/2 I omega squared. Okay. Now I need to make a substitution, so I have to remember that velocity is omega times r. So I'm going to make that substitution. I also need to know the moment of inertia again, and because it's a sphere, it will be 2/5 mr squared. So I will plug all of that into the problem and make all of my m's capital because that's what they gave me. So I have mg delta y equals 1/2 m v final squared plus 1/2. Now I put in the moment of inertia, so it's 2/5 mr squared. And now I put in omega squared, and that's velocity squared over the radius squared. The radius squared will cancel. When I multiply 1/2 by 2/5, the 2's cancel, and I have 1/5. So now I have, and by the way, all of the masses will cancel because they are all the same. So what I'm left with is g delta y is equal to 1/2 v final squared plus 1/5 v final squared, because that is v final. And now I have to combine them. So I found a common denominator for 1/2 and 1/5. So we end up with 7/10 v final squared is equal to g delta y. And when I do the algebra, I end up with 10 g delta y over 7. Take the square root of that. I used 10 for the g. So we have 10 times 10 newtons for every kilogram times my delta y, which was 2 meters, change in height, over 7, square root. We may as well look at the units to make sure you understand what's happening with the units. So we have newtons over kilograms times meters. So we have Newton meter over kilogram. A Newton is a kilogram meters over second squared times a meter over kilograms. So the kilograms cancel, and I'm left with meters squared over second squared, which is good because when I take the square root of that, I'll get meters over seconds. So when I do the math, I end up with V final is 5.35 meters over seconds, which is essentially the same answer I got doing all of those forces and torques, but with much less work.